In this DL, we started talking about the model of thermodynamics. Thermodynamics, as the name implies, is interested in thermal phenomena, that is, things that happen in the world that involve exchanges of energy in the form of heat and work that change the temperature of a substance. There are two main equations in thermodynamics that we care about. The first is actually an equation that you've seen before. Usually in this course, we've talked about things like thermal energy and bond energy as two separate energy systems. However, it's also acceptable to put them together into a single energy system and just call them the total internal energy of the system. That's what U is. U is the internal energy of a system. So what is the change in U equal to? In thermodynamics, there are two ways that the internal energy of a substance can be changed. We can either add or remove energy from the substance in the form of heat, or we can do work on the system, or alternatively, let the system do work on its surroundings. Any of these things will change the internal energy of the system. The second equation is the work equation. We'll talk about it in a minute, but I just wanted to write it here. You might not be too happy about seeing an integral sign in an equation, but don't worry. We won't be actually doing the integrals in this class. We're mostly going to be looking at examples that don't actually require us to use the integral. Let's start by thinking about conservation of energy. When we're doing thermodynamics, there are 7 quantities that we care about. All of these quantities relate back to the energy of the substance in some way, but there are key differences between them. In thermodynamics, there are 2 main types of quantities. The first type of quantities are called state functions. State functions are just things that we can measure about the system that only depend on the system's state. For a state function, we don't care how we got the system to that state. We only care about what the state is. We also have quantities that are known as process functions. Process functions involve the actual process that takes the system from one state to the other. Let's see the difference by thinking about all these quantities. Let's start with temperature. How do we measure the temperature of a substance? Well, we have a device known as a thermometer. And if we have the correct thermometer, we can just put it in the substance and allow it to read the temperature. The question becomes, will that thermometer read a different reading depending on how the substance got to the state that it's currently in? The answer is no. The temperature of the substance is just a number that we can measure directly. We don't need to know anything about how the system got to its current state in order to measure the temperature. So temperature is a state function. I'll represent state functions by this purple star. Which of these other quantities are state functions? Well, let's go from left to right and ask, what about the thermal energy of the substance? Well, we can't measure the thermal energy of the substance like we can measure the temperature. But we learned in the last couple DLs that there is a direct relationship between thermal energy and temperature. If we know the temperature of a substance, we can determine its thermal energy exactly. It does not depend on how the substance got to the state that it's currently in. And so thermal energy is also a state function. So we're left with bond energy, heat, internal energy, pressure, and work. Which of these are state functions? All of these quantities with purple stars are state functions. They can either be measured directly without knowing anything about how the system got to its current state, or they can be determined from those directly measurable quantities. So what about Q and W? Why are they not state functions? Well, because Q and W are the ways in which we take a system from one state to a new state. For example, suppose that all we were measuring about the system was its internal energy. Because internal energy is a state function, it just depends on the state that the function is in at a particular moment in time. How do we change that state? Well, we do that by adding heat and work to the system. Once we've done that, the system will be in a new state. It does not make sense to talk about the heat of the substance at an instant in time. Heat always involves changing something about the substance. It's the same thing with work. We can't say how much work a substance has. We can only say how much work we did to the substance as we moved it from one place to another. So now let's talk about work. Work turns out to be very important when we're thinking about thermodynamics. The reason is that a lot of thermodynamics has to do with how gases change over time. If a gas changes its volume, then it will be either doing work or having work done to it. There are a ton of thermal phenomena that involve changes in volume. Here's our equation for work. This says that if we take the pressure of the gas and integrate it from the initial volume of the gas to the final volume of the gas and make it negative, we'll find the work done on or by the gas. But we have a much simpler version of it here. The reason we sometimes need an integral is because the pressure is not always constant. But in this class, if work is being done, we'll mostly be concerning ourselves with constant pressure systems. If the system is at constant pressure, then the work can just be determined by this. We take the pressure, multiply by the change in volume, and then add a negative sign. Let's think about what happens if the change in volume is positive. As an example, imagine blowing up a balloon. The volume of the balloon is increasing, and so there's work being done. Will this work be positive or negative? Well, the pressure is always positive by definition. But what about the change in volume? Well, we already said this is an expansion. The balloon is getting larger, so the change in volume will be positive, and the work will be negative. But what does this mean? It means that in order to expand, the gas inside the balloon has to expend some of its energy in order to increase its volume. The internal energy is going down. What about something that involves a decrease in volume? Well, a decrease in volume is the exact opposite. Instead of negative work, there's positive work being done. This means that the outside environment is pushing on the system and causing it to get smaller. This will tend to increase the value of the internal energy for the system. But there are ways of representing this information that's a little more visual. These are known as state diagrams. State diagrams are just graphs of state functions. Let's look at an example. Here's an example of a state diagram. This is known as a pressure volume diagram because the two state functions that we're looking at in this diagram are pressure and volume. The states that we care about for a PV diagram are represented by points on the graph. Each point represents a particular pressure and a particular volume, and therefore represents the state of the system. The lines that connect the points are known as processes. They're the way that the system gets from one state to the other state. How could we represent work on this diagram? Well, remember that work is an integral over pressure and volume. What is an integral when we're thinking about a graph like this? Well, it's just the area that is under the line. So if we wanted to calculate the work for this process, we could do so by calculating this area. The value of this area would give us the work done during this process. But would it be positive or negative? We know that when volume increases, work being done is negative. And when volume decreases, the work being done is positive. So is the volume increasing or decreasing in this process? This is why it's important for us to identify which state is the beginning state and which state is the end state. I've written this state as the beginning state and this state as the end state. So the volume of the system is increasing as it goes from left to right. And so this work will be negative. If we had flipped them and put the beginning state here and the end state here, the value of the work would be the same because this line would still be the same line. However, the work itself would now be positive instead of negative. Here we can also see why work is known as a process function. What would happen if instead of taking this route from state 1 to state 2, we took a different route? Notice the area under this line is not the same as the area under this line. The initial and final states of the system would be the same in both cases, but the work done by the system is less for this lower line than it is for this upper line. There's one other type of state diagram that we're going to be using a lot. This is what's known as a UT diagram, where U is the internal energy of the system, while T is its temperature. What's some interesting information we could get by drawing a graph on a UT diagram? Let's suppose we collected this data. These points represent specific states of the system, where the internal energy is a certain value and the temperature is a certain value. One thing we very often like to do with data like this is try to find a best fit line. So let's draw that approximately. Well, what does this line tell us? Let's think for a moment about the slope of this line. You may remember that a slope of a line is equal to a rise over run. If we wanted to calculate the slope of this line, we take the difference in height between the beginning and the end of the line and divide by the difference in the horizontal position for the beginning and the end of the line. Let's think about what the units of this would be. Well, what are the units of the vertical position of the line? Well, we know that the vertical axis measures internal energy, and energy is measured in joules. So the change in the height of the line has units of joules. What about the change in the horizontal position of the line? Well, the horizontal axis measures temperature, and we measure temperature in Kelvin. So if we divide a change in the height by a change in the horizontal position, we will get a number with units of joules divided by Kelvin. But what's another number that we know of that has units of joules divided by Kelvin? The answer is heat capacity. Heat capacity tells us how much energy we have to add in order to change the temperature of the substance by 1 degree Kelvin. Thermodynamics is super useful in a ton of different areas, so we're going to continue studying it next time in DL. We're going to use these quantities to determine some other interesting things about a substance, including how we find heat capacity when we're holding pressure constant instead of volume.